Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
I'm Drew, and this episode is about a different aspect of the future of the internet. The potential of this 6G internet is massive, coming with revolutionary speeds and much more potential for data transmission. However, with this additional innovation comes further challenges, particularly with the connections between different devices in the spider web of the internet. Every time you send a message, stream a video, or load a website, that information has to travel through a network. And that network has to make constant decisions about where your data should go. Which path is the fastest? Which route is the least congested? Which option balances efficiency and reliability? That decision-making process is called routing, and it turns out to be one of the hardest problems in modern communication systems, especially as our systems get more and more complicated with 6G internet on the horizon. Now here's where things start to shift. As networks moved towards 6G, they become far more dynamic. Instead of relatively stable systems, we're dealing with environments that are constantly changing. Devices are moving, demand is fluctuating, and the network itself is expected to adapt constantly. Traditional algorithms, the ones we have worked on for decades, start to break down under that level of complexity. So researchers are beginning to seek an entirely new solution to this routing issue. New types of internet are being explored. Researchers are using deep reinforcement learning to find optimal routing routes in our new systems. Instead of relying on fixed rules or pre-designed paths, reinforcement learning allows a network to learn from experience. It tries different routing decisions, observes the results, and gradually improves over time. The network is constantly asking itself, what did it do well, and it tries to continue doing those good things. This simple idea will become incredibly powerful when the systems become as large as they one day will. Reinforcement learning is built for exactly the kind of complex, dynamic environments that 6G internet is going to provide. It doesn't need a perfect model of the system ahead of time. Instead, it adapts as conditions change, making decisions that balance speed, reliability, and efficiency. But this introduces new challenges, which is why researchers are working to optimize the application of these new ideas. Oumayma Bouchmal is a researcher specializing in these next-generation communication networks. She completed her PhD in electrical engineering at Eindhoven University of Technology, where her work focused on using quantum algorithms to solve complex routing and resource allocation problems in 6G systems. Her research explores how quantum computing can be applied to the real world, especially in systems that are far too complex for our traditional approaches. In this interview, we're going to break down what makes 6G routing difficult, why classical methods fall short, and how potentially quantum computing might offer a new way forward. Can you explain what problem you're trying to solve when it comes to the future of 6G networks?
Okay. Yeah, that's a very interesting question because, well, as you might know, 6G networks are still something under development. So it's not something that is implemented yet. In fact, we are still trying to implement 5G networks, and 6G is still under, how to say, under constructions, if we can say. But based on what we have learned in 5G, or what are the problems that we saw in 5G, we were expecting that also this problem will remain in 6G. And one of these problems that I found quite interesting are optimization problems in general, because optimization problems are, how to say, very famous to be somehow NP-hard problems. And we do find a lot of NP-hard optimization problems in 5G networks already, like, for example, routing. So this like in 6G, I think one of the main, how to say, hard problems, or the things that we are going to struggle with the most are optimization problems.
And in your paper, you describe these 6G networks as very dynamic and complex. What specifically makes routing in 6G much harder than in previous generations?
Okay. So as I said before, routing can be described as a combinatorial optimization problem. And we know about combinatorial is that when you add one variable or one option, one extra option to your problem, the number of combination or the number of options increase exponentially with the number of combinations, right? So for example, like if you have, if you want to travel from one country to another, and then you have like some kind of like options, either to go from this path or that path or that path, this is already a hard problem. But imagine if I add you another option on the top of that. So the number of combination increase with the number of variables we have. And what makes this network, so the question is like, what makes 6G networks very dynamic, right? So you can think of it as, so now if we look back to probably our parent generation or even before our parent generation, you are pretty young, but for me, in fact, when I was in high school, for example, we did not have like very fancy phones. We have like these Nokia phones that's, you know, you have, you can't even, you don't have no video calls, no nothing, right?
No, no.
So exactly. So in fact, with 6G, the G in 6G means generation. So every 10 years, we have a new generation that we are expecting will be better than the previous one. So we have 3G, then we have 4G, and then we have now 5G. That's, as I said, we are still trying to implement. And with this generation, we are already reaching so many use cases and applications that we did not have in 4G, for example, like the video calls, the very high quality video calls, the video games, etc. Also like this, how to say, like being able to have this remote operation. So for example, a doctor in China is capable of doing an operation in USA, etc. So this type of application we did not have in 4G. And in fact, it's still somehow not fully implemented in 5G. So what makes these 6G networks very dynamic and very complex is what we are expecting from these networks. So as I said, with every generation, we want more. So we want better use cases, more, how to say, fancy applications, and also our, what we call the quality of service of this application needs to be very high, which means that if you are calling your friend a video call, you don't want to be like, you know, waiting for this connection to do like this. No, you want to call him or to call her, and then she's able to pick up, and then you are able to have like a real-time conversation. So this real-time conversation does not come from nothing. It comes from an infrastructure that needs to be very robust. It needs to be able to deliver for you what you want. So this dynamicity and complexity comes from usually what we expect from these 6G networks, which are these very, very fancy, complex type of use cases and application.
Thank you. So your work focuses on software-defined networking. For someone like me hearing that term for the first time, what is SDN and what does it do?
Okay, so probably just like to clarify this, my work does not really focus only on SDN. So in fact, when I wrote the paper that you read, which is like from classical to quantum review on software-defined networking, right? I started with software-defined networking because it is the state of the art. It was, it is, and I think it's still going to be the state of the art when it comes to the new approaches that was implemented in order to make our networks more, how to say, more capable of delivering this application that we are looking for. So the idea behind software-defined networking, so in order to explain to you the idea of SDN, let me go back and tell you how networks was before SDN. So usually, if you go, like, we have like this very, how to say, like this, you open and then you find, if you look to network topologies or something like that, you find like some routers connected with some links, which are usually like optical links. And then if you want to send the data from router 1 to router 10, you just need router 1 will need to check who are like the neighbors or to whom it is connected. then etc., then etc. So everything was happening inside that thing. But what SDN provide is something a bit more, let's say, not a bit, in fact, is way more smarter. So what we did is that we decided that instead of that every router takes a decision and then deliver to the next one, and then the other one then look into to whom I am connected, then deliver to the other one, we are going to have an entity like someone that is way smarter, that is like on the top and looking of what you have in the infrastructure. So we removed what we call the brain. We separated the brain from the dummy routers. And we call them dummy because they are no longer smart. What they do is just to follow what this brain is going to tell them to do. And this brain is the controller. So in the SDN, you have two parts. You have the SDN controller, where all the smartness is, and then you have like the dummy devices, which is the data plan. And then this controller is the one that takes decision of routing, is take decision of allocating resources or scheduling, etc. So SDN is basically the separation between the data plan and the control plan. And the control plan is the brain that takes all the decision, and the data plan when you have your routers, your switches, etc. And they are the one that like just follow what this controller is going to tell them to do.
Awesome. And that makes routing in 5G or 6G much more efficient, right?
Kind of, yes. It was, in fact, SDN was one of the solutions that was introduced in order to make not only routing, but like a lot of functionalities of the network more efficient.
Awesome. So another major part of your research looks at reinforcement learning and deep reinforcement learning. How do these help a network make better routing decisions and make it more efficient?
Yeah. So I talked about, in fact, in my paper, I talked also about all the type of machine learning, but probably reinforcement and deep reinforcement learning more because also they were the state of the art. So if we go back to your very first question about what makes this network very dynamic and very complex. So as I said, these networks are very dynamic and very complex. And in order to have like a normal machine learning algorithm, like supervised or unsupervised learning, you need to have like some data in order to train your machine learning algorithm, the supervised one or the unsupervised one. But since these networks are very dynamic, you cannot predict how they are going to be. So you cannot predict, you cannot classify, you can't do like a normal machine learning algorithm. And this is where reinforcement learning came. So the idea of the reinforcement learning is that you are learning from the environment. Whatever your environment is, you are going to send your reinforcement learning agent. The reinforcement learning agent is going to learn from this trial and error loop, and then it's going to tell you what is the best action that you can do. So this is the idea of the reinforcement learning. So you have this, error and trial loop. You try, you learn, you improve your reward function. You try, you learn, you improve your reward function until you have it like, the perfect reward that you can get. But then, since again, these networks are very, not only complex and dynamic, but also they are very large. And so, for example, like in our generation, not everyone has a phone, not everyone has a laptop. But now at least you have a phone, a laptop, a tablet, a gamer. So
Yep.
one user have them all, right? So we have these networks are also very large and very dense. So in order to wait for the reinforcement learning to go, to learn, to maximize or to minimize your function, your reward function, or whatever optimization problem you are plugging into your reinforcement learning agent, it takes time. And one of the solution to this it takes time thing in optimization problem is doing approximation. So instead of looking into the most optimal reward function we can get, we can approximate a good enough reward function. And this is the role of deep reinforcement learning, because in deep reinforcement learning, you have the neural network. And the role of this neural network is basically to approximate, to approximate your reward function. So let's say that I will give you again another simple example just to understand that. So if you want to travel from, let's say, from Barcelona to Sevilla, right? There are plenty of routes you can take. I can give you a reinforcement learning agent that will take, let's say, 2 days in order for you to find the perfect path that is going to take you how to say, like so few times to reach, and also is not going to consume too much gas, right? This is in 2 days, he's going to give you this. But what if I give you a deep reinforcement learning agent that instead of 2 days, is going to take 2 hours, and then you will find your, how to say, good enough path in order to reach Sevilla. Are you going to wait for 2 days, or you will take the 2 hours, and then probably in 2 days you will be already in Sevilla eating tapas? You will
Uh,
you will take
two
the
hours.
deep reinforcement. Exactly. So this is the idea that why most in our community now people are shifting from reinforcement to deep reinforcement learning, because sometimes you don't want the perfect solution, you just want a fast, good enough solution for you. And that's the idea of deep reinforcement learning.
You also touch on quantum machine learning as a possible future direction. Could you give
Yeah.
us a rundown of what that is and how it works specifically?
Oh, yes, sure. In fact, my whole PhD was about quantum machine learning, and the SDN and the reinforcement learning was the introduction. So I I will pick up from where I left, which is the deep reinforcement learning and the approximation. So the idea of, or the limitation of deep reinforcement learning, it's good, it's amazing, but to train these neural networks, it takes so much time. So when these neural networks are trained, you can have your solution fast. But before that, you need to do some training and some tuning, etc., etc. So now people were thinking, okay, what should we do? How can we make this training fast? Do we have other tools that can probably make our machine learning, how to say, more efficient? And this is where quantum computers come. So quantum computers are promised to, how to say, to speed up several operations. So people were thinking, so what if we take quantum computers and run machine learning algorithms with it? So quantum machine learning is basically the combination of quantum computers within machine learning programs. So how can you implement some machine learning programs into a quantum computers? And this is from where the concepts of quantum machine learning came. And it is not that simple, because it's not only implementing a machine learning algorithm, because machine learning are classical by default. So you have these classical machine learnings. So what you need to do is basically to convert this classical machine learning into something the quantum computer can understand. And this is what we call the encoding process. And then after that, you can run this on a quantum computer. And what we expect, or what we hope at least, is that the process will be way faster than if you do it on a classical computer. So this is the idea of quantum machine learning.
Hmm. So you mentioned time and like training this AI technology as a limitation for deep reinforcement learning. What challenges arise when we try to use quantum methods for routing?
Oh, a lot, a lot, a lot. In fact, because quantum computing in general is still a very, I should say, it's still in the very early stages. So the first and the most famous limitation that we have now, and we are trying to, to deal with, is basically what we call the volume of the quantum computers, which means that the current state of the art in quantum computers, we don't have too many qubits. So I think the state of the art is IBM quantum computers with Osprey, I think the name of the machine, if I am not wrong. Well, the one with 1,120 qubits. So this is the state of the art of quantum computers. And this is not enough, because when we talk about something we call the supremacy of quantum computers, or the advantage of quantum computers, we are expecting something in around 1 million qubits, and we are still in the thousands. So the first limitation is basically the number of qubits. The second limitation are these quantum computers are not perfect. So we are now what we call the noisy intermediate scale quantum computers, which means that these computers are very noisy. So even if, ideally speaking, or theoretically speaking, or based on quantum physics, these hardware are supposed to provide some kind of speed up. It's supposed to solve some kind of problems better than classical computers. But in practical, we are still a little bit far from this because of the noise. So they are very noisy, and it is not easy to scale up these quantum computers because the technology is not, the fundamentals is not the same. So these hardwares are based on quantum mechanics. So it's a bit hard to scale up from 1,000 to 2,000 because of so many things. And so the first one is basically qubit counts, which are the number of qubits. We have also the number and the quality of the quantum gates that are implemented or are provided by quantum computers. So we have some basic gates, but we don't have all the sets of gates in a quantum computer, which means that you cannot implement whatever algorithms you want. So there are like a list of what we call the zoo of quantum algorithms, when you find all the type of quantum algorithms that are basically designed to solve several problems better and faster than classical one. I think probably you know Shor algorithm, Grover algorithm, the quantum Fourier transfer, etc. But we cannot really implement for now this algorithm on a quantum computer because we don't have the gates we need in order to implement them. Another probably problem that I also faced a lot when I was doing my PhD, which is the standardization, and also how to say. So since quantum computing is still in the early stages, and even worse, implementing quantum computing based solution for networking or for 6G, 5G, whatever, it's still like in the very, very early stage. You can't really find something that can help you. So when I was doing my research about how to implement some quantum solution for routing, for example, you cannot find many things in the literature to help you. So you are basically doing everything by yourself, which can be very challenging for some people. Now I gotta say that it's a big difference because, I mean, the paper that you read, I wrote it in 2022, and now we are in 2026. So a lot of things happen in 4 years, and there are a lot of research going on, and also a lot of people now are interested in quantum computing, and they start to believe in quantum computing. But back then, most of people were like, what can you do with 100 qubits? It's basically nothing. I mean, which makes sense because what we were implementing is a graph, for example, of 5 qubits, 5 nodes and 6 edges. And you are like, Dijkstra can solve this problem way faster than a quantum computing. Why I should bother? But the idea is not about that. The idea is that, as I said, when you have this very highly dynamic network, when you have this situation, when you are like not only solving a shortest path problem, but you are solving a multi-objective, multi-constraint optimization problem, and then you have hopefully this, what we call fault tolerance quantum computer, then you can really achieve the quantum advantage you are looking for, and you can, provide the quality of service requirements that we are expecting from these networks.
Well, thank you so much for your time and your insights. I appreciate it.
No problem at all.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.